Greetings, this is a short little supplementary video to go with discussion question number 10. So in discussion question number 10, we introduce this new number, this number e. And it's really actually turns out to be a very important number. And if you're going to go on to mathematics, you're going to see this constant quite a bit. And actually you'll see it in chemistry, you'll see it in physics, you'll see it in econ, you'll see it in biology, you'll see it in sociology, you'll see it in probability and statistics. Actually, this number shows up all over the place. In one definition, there are several, but this is one of the most common ones. One definition for this number is this, is that e is equal to the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. So let's dissect that a little bit and see if we can figure out what the heck that means. So what limit means is it says take and push something. Push something to where I tell you to. And in this case, they're telling you to push n, take n, I want you to push that to infinity. Make it really, really big. So let's see what happens when we do that using our calculator. So let's go grab the calculator here real quick. Let's go into the y equals menu, clear out any craziness we happen to have in there, and let's take the function we're supposed to be pushing n to infinity in. So that's going to be parentheses 1 plus 1 divided by, well, we're going to use x on the calculator, and then raise that to the x power. All right, so the easiest way for us to go ahead and push that to a really big value is going to be to use our table, and in particular we're going to go in and set, using the table set here, which is second function above window, we're going to set our independent to ask. We'll go in and say, hey, you know what, I want to tell you what numbers I want to put in. So once I do that, when I go into my table, you notice now my table is blank and allows me to input values. So let's go put in some large values of x and let's see what happens to that function 1 plus 1 over x raised to the x power. So let's start off, relatively big. Let's put in 100. And we notice we're already at 2.7. If you've read, hopefully you've read, if you're watching this, you've read the lab, you notice that it's 2.7, 1828, 1828, 4590, 45, etc., etc. And so even at x equal to 100, we're already good out to one decimal place, 2.7. Well, what if we got to 1,000? Well, now we're at 2.71. Well, let's go up to 10,000. So let's keep going up by powers of 10 here. And now we're at 2.7181. Oh, we're getting really close. So notice is that the larger values of x that we put in here, the closer and closer this expression gets to being equal to e. So we'll go to 100,000. We'll try that. And we're starting to get really close. Okay, so that's the idea, is that, let's go back over now to our drawing here, is that as n goes to infinity, as we push n to a really large number, this limit right here, this number right here is going to approach the number e. Okay, all right, now where is this number good for? I mean, what do we use this thing for? Well, the number e shows up in all sorts of real-world applications, as I was discussing earlier, but there's one model in particular that you will come across in lots of different disciplines. It's sometimes referred to affectionately as the PERT model. And it says that P of t, or the population or percentage or parts or whatever that you're going to get with respect to time, is equal to, here, let me clean my stuff up. I'm going to start over here. P of t is equal to P sub 0 e to the RT. Okay, now that turns out to be an exponential function. Why is it an exponential function? Well, because the variable t is up here in the exponent place. So that's an exponential function with a base of e, okay? So how do we use this model? Well, a couple things to know about it before we get started. We know that P of t, that's going to be how much you have at time t. So that's the amount at time t. At time t, okay? So this is a good place to be taking notes if you're not already. P sub 0, that's equal to the initial amount. And R, that's our exponential rate. Could be either growth or decay. So let's take a second, let's talk about that. So at the exponential rate, if R is greater than 0, then you have growth. If R is less than 0, in other words, if R is a negative number, you have decay. Okay, so let's just do a brief example of this. Let's say I give you P of t is equal to 3.20 times e to the negative 0.123 t. Okay, well, that's going to be an exponential decay function. In other words, our initial amount here, our p sub 0, is equal to 3.2. I actually didn't need to give you that trailing 0, did I? And then our rate r here is going to be equal to negative 0.123. And so I can ask you, for example, what is p of 2? Well, p of 2 is going to be equal to 3.2 times e to the negative 0.123 times 2. All right, so let's go see how to actually do that on our calculator. Let me go ahead and shrink the screen up here so we can do two things at once. So that's going to be 3.2. And it turns out that, look right here, we see ln. The second function above ln is e to the x. So you hit second and then hit ln, and you get e to the x, and then we get negative 0.123 times 2. Okay, and we hit an enter, and we get back 2.502. So the amount left after 2 time units, let's go get that number again, let's go out to just 3 places, 2.502. Got to look at it a couple times just to make sure I got it right. Okay, so that's enough for this first one. There are several more parts to these videos. Go ahead and watch them all. You will find them very helpful in understanding the discussion questions.